Okay, so in the last video, I'm actually just continuing the notes here. In the last video, we talked about LTI systems. Okay, we defined a system, and then we talked about two important properties for us in ECE 45, which are linearity and time invariance. Okay, and we described those definitions, so definitely check out that video if you missed it. Now we're going to go over some examples. Okay, so I'll call this linearity and time invariance examples. Okay, and this doesn't mean that every example we do today is going to be of a system that is both linear and time invariant. Actually, it's definitely not the case. I want to show you some systems that are linear and time invariant, so LTI, or maybe just linear and not time invariant, or vice versa, and so on. So it turns out that any combination can work, meaning there's some system out there that is either both linear time invariant, only one, only the other, or neither. Okay, I'm going to go over 3 of those 4 cases, and then I'll leave the last one for you to try and come up with an example on your own. It's not, I mean, there's infinitely many examples for all of these, so it should be totally fine. And that would be a good check to make sure that you're keeping up with all of the content. Okay, so let's look at the first example. So this is going to be of what's known as the differentiator system. So I have some system here, I'll call it the differentiator. And what does the differentiator do? Well, you can imagine it differentiates your signal. Okay, so I put x of t into the system. What do I get out? I get out the derivative of x of t. Okay, x of t in, I get out the derivative of x of t. Okay, so we want to check and see, is this system linear and is this system time invariant? So let's start with linearity. And this is why I'm doing it on the same page of notes I started before. Let's refresh ourselves on the definition. So a system is linear if whenever I have 2 inputs that produce 2 outputs, y1 and y2, then what does it mean for our system to be linear? That means if I multiply x1 by some constant a and add it to x2 multiplied by some constant b, then I should get the same, as we say, linear combination of the outputs of x1 and x2. So a times y1 plus b times y2. Okay, and this has to hold, of course, for any choices of the constants or the signals. So how do we check if a system's linear? Well, we have to follow this setup. We have to say, all right, let's suppose we have 2 arbitrary inputs. We don't know what they are, and they produce whatever outputs they produce. And then we have to put this signal into our system and see what comes out. And if what comes out is this signal, meaning the same linear combinations of the outputs we wrote, then the system's linear. Otherwise, it's not linear. Okay, so let's do this. So what do we want to do? We want to suppose we have 2 inputs, x1 and x2. And we're going to put them into our system, and they're going to produce some outputs, which I'll call y1 and y2. And we know what the system is here, right? So what's the output from x1? Well, it's its derivative. What's the output from x2 that I'm calling y2? It's just the derivative of x2. Okay, just following the rule of the system. All right, so what's the next step? Now we have our 2 arbitrary inputs. Now we have to test what happens when I multiply x2 by a constant a and add it to, or sorry, when I multiply x1 by a constant a and add it to x2 multiplied by some constant b. So I got to put that into my system and see what happens. Okay, so then let's write that down. A times x1 plus b times x2. That's going to go into my system. And what am I going to get out? Okay, what am I going to get out? Well, if you're ever confused about what you get out from your system, I have this trick that I use a lot that I think makes it really, really easy. So it's kind of confusing what's happening here. We have a lot of symbols. We have a lot of functions. Okay, let's just call this entire thing some other function. I always like to use x hat of t. I know that that is just going to be my input, whatever it is. And let's see why that's useful. That's useful because if I take this function x hat of t, which I've made equal to that input we were curious about, it's very easy to tell what the output is. Why is it easy? We just go to our definition of the system, and everywhere we see x, this is why I like x hat, just put a hat. So I put x hat of t in, that's exactly what I have, and I get out the derivative of x hat of t. Okay, so that's why if you're given your input-output relation, it's very easy to use this kind of hat system. I mean, nothing profound is happening. It's just a notation thing to make sure you don't get confused, because some of the examples we do can get a little confusing. Obviously, this one is simple enough that I think you don't need this method, but I wanted to demonstrate it on a simple example so you really get what's happening. Okay, so I just gave this whole input a new name, and that allowed us to easily find the output. And now I just have to plug back in for what that function was. So now I see my output should be the derivative of that function. So I'll open some parens here. And it should be the derivative of whatever x hat of t was. But look, we have that written right here. It's ax1 plus bx2. Okay. Now, what are we trying to find here? I mean, what's our end goal? We could just sit here and simplify all day, but what we got to keep in mind what we want. And what we want to happen is we want to get this expression we have into a form to decide whether it equals this or not. So that's a times whatever output I get from x1 plus b times whatever output I get from x2. Okay, so we got to decide, is that equal to that expression? Let me just write over here what that expression would be. This is what that expression would be. We want to decide if this equals this. Obviously, it's not clear yet. Let me write in what y1 and y2 are. They're just the derivatives of x1 and x2. So we have a times the derivative of x1 plus b times the derivative of x2. And this would not be necessary to do if you were actually solving the problem, just trying to make sure we all understand what's happening. This is the function that if our output is actually equal to this function, then the system is linear. If it's not, then it's not linear. So that's where we have to try and check. So right now we're at this stage, and what can we do? Well, it seems pretty clear. We'd like to take that derivative and distribute it through everything in parens. And we know that differentiation, you can do that with. You can, the derivative of a function times a constant is just that constant times the derivative of the function. And the derivative of a sum of two functions is just the sum of their derivatives. Okay, this is basic calculus facts. So we know that the derivative of this entire thing is just a times the derivative of x1 plus b times the derivative of x2. We're proving linearity for the system, and we're using linearity of the derivative from calculus that we already know. And now you can see that's exactly what I have here. So just to complete the problem, I will substitute back in for these two derivatives, which we know are equal to y1 and y2. It's exactly what we did to get from there to that step. Okay, I kind of started at the end to try and illustrate where we wanted to go, and now we've actually gotten there. We have a times y1 of t plus b times y2 of t. Okay, I just kind of did the step I'm about to erase, but the other way. And there we go, we've done it. So we've shown that a times x1 plus b times x2, when I put it through my system, notice that arrow, I did not write equals there. I wrote an arrow to say this is the input to the system and this is the output. Okay, maybe I should have mentioned that. I'm not sure if I've mentioned that in a previous video. Up here, I like to draw the system just so we all know what's happening. But then when I do problems, I don't want to keep drawing that empty box everywhere. Sometimes I might do it, but often we just use an arrow. And that means this is the input to the system and this is the output. Okay, so we put this in, ax1 plus bx2, and we get out ay1 plus by2. And x1 and x2 and a and b were completely arbitrary. We didn't put any restrictions on them. So let's check if this satisfies the definition of linear, and it does. Because we said if x1 gives us y1 and x2 gives us y2, then if you put any linear combination of x1 and x2 into the system, you should get out the same linear combination of the outputs. And that's exactly what we've shown below. And so at this point, we can conclude. The system is linear. We've proved it. Okay. So great. So that was linearity. Now let's do the same thing for time invariance. Okay, so let's refresh what the time invariance definition was. The system is time invariant if when I put in some input x of t and get out some output y of t, then if I put in any shifted version of x of t, okay, so time shifted, I mean, x of t minus some constant t naught, then the output has to be the same shifted version of the output. So I should get the output I got before, y of t, just shifted by the same amount, t naught. Okay, and again, it has to be true for any choices of t naught and x of t. So let's test that out. So we're going to follow a similar pattern here. Let's suppose we have some input x of t, and it gives us an output y of t. It's exactly how the time invariance definition started. And again, we know what this output is for this system. It's the derivative of x of t. So now what do I want to do? Very similar to linearity. Now I want to put this signal into my system and see what happens. Let's see if I actually get this on the output. Let's do it. So then I put x of t minus t naught into my system. And again, this example, you can probably do it without this step, but I just want to illustrate how nice it is to give this a different name to easily get the output and not get confused, because we're going to get into examples that are more confusing. Okay, so I'm just going to call this x hat of t. And again, we know what x hat does when it goes into the system. We can just use our input output definition above and hat everything. So I know when x hat goes in, I get the derivative of x hat out. Now I can plug in for what x hat is. X hat, I know by definition here, is x of t minus t naught. Okay. Now the question is, what is the derivative of a shifted function? So if we think about it, let's say, I don't know, let's say I have some function like that, and it has some derivative. What happens if I shift this by same amount, by some amount? Okay, what happens if I shift it to the right by some amount and take its derivative now? That's exactly what we're doing. I shift the function and then take its derivative. Well, you can imagine that the answer is just the same derivative I got before, but shifted. Right? If I shift the function and take its derivative then, it's the same derivative I would have gotten initially, just shifted by the same amount. It's just the derivative over here now. And that is essentially saying that differentiation is time invariant. That's exactly what we want to prove. I just sort of said it in words. Okay, but that's just a basic, attribute of taking derivatives of functions. So the way I'm going to write this here is that this is the derivative x prime evaluated at t minus t naught. And this is just by calculus, we know this. Okay, so we're using calculus here because, we're using differentiation. Let me write it here too. This is by calculus. Okay. So the derivative of a shifted function is just the derivative of that function shifted by the same amount, is all I'm saying. Okay, make sure that makes sense. And now what can we conclude? Well, we can conclude, hey, wait a second, y of t is the derivative of x. This is just x prime of t. So if y of t equals x prime of t, here I have x prime evaluated at t minus t naught. That's just y of t minus t naught. Okay, so wait a second, I put in x of t minus t naught and I got out y of t minus t naught. Hey, that's exactly what the definition of time invariance says. When you put in a shifted version of your input, you get out the same output you got before, shifted by the same amount. That's what time invariance says. Okay, in other words, the system's sort of invariant to time. If I put something in and I know what the output is, and now I just put the same input in, but shifted to a different point in time, it's going to be the same output I got, but shifted by the same amount. So it lines up with how I shifted my input. Like that makes a lot of sense, right? That's a nice property to have. So it turns out it's true for the differentiator. And so the system is TI. Okay, so differentiation is both linear and time invariant, so it is an LTI system. Okay, when we say a system is LTI, we mean it's both linear and time invariant. Okay, great. Let's do another one. What's the next natural system we want to look at? Well, I think probably the integrator. Okay, so what does the integrator do? Well, it's going to integrate all the way from negative infinity up to some value t, this function x of t. Now you can see here I'm using the t variable for the upper limit. Okay, so I can't use t anymore in the integral, so I'll just use tau. Okay, so this is my output that I call y of t. Okay, so you can see this t actually appears in this upper limit. The argument to the function tells you what point to integrate your function x up to. Okay, so that is what this integrator is doing. So if I put in some x that looked like this, and I wanted the output at this value t, okay, then the output at that value t would be this integral. It would be the area under that curve, up to that point t. That's what this is saying. Okay, so this is the integrator. And let's check the properties. So linearity. Okay, I tried to go really slowly in the first example, so I'm going to pick it up a little bit here. So we know what we have to do. We have to have two arbitrary inputs. So x1 of t is going to go into the system, give me y1 of t, which is going to be this integral. All I'm doing is writing out the definition of y of t. It's the integral of this function x that I put in, but now I put in x1, so I have x1. And we also have an arbitrary signal x2. It's going to give me y2 of t. And now I put x2 in the integral. Okay, so these are my input and output. Then what do I need to do? I need to look at an arbitrary linear combination of x1 and x2. And again, I'm going to call this some new function, just so I don't confuse myself. Okay, it's so nice and simple when you call it some new function, because now I just hat everything. I see exactly what I need to do. The output here is just going to be the integral from negative infinity to t of x hat of tau d tau. Oops. And now I can plug in for what x hat is. I know what x hat is. Here's the definition. So x hat of tau, I just put a tau everywhere I see t. I get a x1 of t, or sorry, tau, plus b x2 of tau. Okay, d tau. And now we're going to make a similar step as we did in the differentiator, right? Here's where we are analogously in the previous problem. Now we used properties of the derivative from calculus to split that derivative up, distribute it through. Let's do the exact same thing with integration. So by calculus here, we're going to take this integral and distribute it through this integrand here, because we know from calculus you're allowed to do that. So we're going to get a times the integral of x1 of tau d tau plus b times the integral of x2 of tau d tau. And now what's our final step? What did we want to conclude if the system was linear? We wanted to see, does this equal a times y1 of t plus b times y2 of t? Is that the case? Well, let's look. Y1 of t is this integral. Wait a second, there it is. This is y1 of t. And so this is also y2 of t. And so yes, there we have it. So this equals a times y1 of t plus b times y2 of t. And so the system, I'm just going to write linear check. System is linear. Yes, check. We checked it. Yeah. So you can see how similar this is to the last example. Now let's check time invariance. Okay, let's check time invariance. So we're going to suppose x of t gives us our output y of t. We need some arbitrary input to work with here. That's what it is. Now I want to check what is the output when I put a time-shifted version of x into my system. And x of t minus t naught goes into my system. And again, I'm going to call this a different name. I really recommend this. You'll never get confused. Sometimes it can get very confusing. Like, for instance, if the output is also sort of messing with the time argument, it can be confusing what happens when I'm putting in a function that already has something changed in the time argument. So I really recommend just giving it another name, x hat of t. Okay, because now we can easily find what the output is, just like we did before. I get the integral up to t of x hat of tau d tau. I'm going to erase these hats here. Okay, and now I want to work with this function. So I'm going to plug in for what x hat of now tau is. So I'm putting tau into this argument. So everywhere I see that t, I want to put tau. So I'm going to get x of tau minus t naught d tau. Okay, so that is my output. And let's remind ourselves what we're trying to check with time invariance. We're trying to check whether when I put a time-shifted version of my input into my system, I get a time-shifted version of my output. So let's very quickly just try and see what would this function be. Okay, sometimes it can be hard to know what step to make next to simplify this. Let's jump to the end and see what that function would be. Let's take a look at y of t minus t naught. What is that? Well, the only place t appears is in that upper limit. So I'm going to get the integral from negative infinity to t minus t naught, x of tau d tau. And the question is this equal to this? That's our main question. This right here is the output for my shifted input. This is the shifted version of my original output. And time invariance asks, are these things equal? Okay. Are they equal? Now, at first glance, you might say, well, they sure look different, right? They sure look different. I'm not exactly sure what I would have to do to change one into the other. They don't look like the same. But you can't stop there. Just because things don't look the same doesn't mean they're actually not the same. Okay, so they might look different, but they could actually be the same. And it turns out that's the case here. And so how could you ever know for sure Well, you want to try and manipulate one of them somehow to make it look as much like the other as you can. And what is the biggest difference, at least what seems to me to be the biggest difference, is this argument right here. Here I have x of tau minus t naught. The time argument isn't just the integration variable like it is here. So what does that make you think of? If I ever have an expression in an integral that I want to just make the integration variable, okay, we can do a change of variables, or I think as some people call it, maybe a u substitution. I always learned it as change of variables, but I've heard other people call it that. So let's do so. So let's call this whole thing u. And we're going to make that our new integration variable so that it can look exactly like this function that we're trying to decide if they're equal or not. So we'll call that u. So I'll let u be tau minus t naught. And that means du is d tau. Okay, and so how does that affect my integral? Well, I'll have an integral of something, and then I'll have x of u du, is d tau equals du. Okay, now how do I change the integral bounds? Well, I just have to look and say, hey, originally tau went from negative infinity to t, so let's see what happens to u. Well, when tau is negative infinity, I have negative infinity minus some constant. Who knows, maybe it's 10. Well, negative infinity minus any constant is still negative infinity. So u still starts from negative infinity. And where does it go to? Well, here tau equals t. So when I plug in t for tau there, I get u equals t minus t naught. Wait a second. Those two are actually equal now, right? Because the integration variable, who cares what we call that? It's called tau here. It's called u here. That doesn't matter. That's just a dummy variable. And you can see that those two functions are actually equal. So this equals y of t minus t naught. And there we go. We see that we shifted our input function and we get the output we got originally, y of t originally, but shifted by the same amount. And that's exactly what we needed for time invariance. This tells us that the system is TI. Yep. Okay. So now we've shown the differentiator and the differentiator and the integrator are both LTI. That's what we've shown so far. And I like these examples because I think they illustrate a lot of the concepts that we're going to see as we go on. All right, these are equal. Okay, great. So let's look at the next one. So the next one, probably some people would call it a squarer, but I'm not going to give it a name. We're going to put x of t in, and we're going to get x squared of t out. Okay, and whenever I put like x squared, all I mean is this is x of t squared. So every value I just square it, but I write it like that usually. Okay, so this is my output. All right, so let's keep going here. Let's test linearity. Okay, so we're going to suppose that, again, I hope this is seeming repetitive and you know what's coming, right? Because I want to make sure that everyone understands exactly how these types of proofs go, because LTI systems are really important for us. So x1 goes in and we get y1 out, which we know the definition, right? You can just put a 1 everywhere. It's x1 squared of t. And we're going to suppose we have some other input x2, and we get y2 of t out, which is x2 squared of t. Okay, let's keep going. So we want to check if some arbitrary linear combination of those two input functions goes into my system, what comes out? Again, I'm going to call this x hat of t. And then we know what comes out, right? I get x hat squared of t. Okay, and remember what I called this function. Maybe I'll write it like this just to be super clear. I get that function squared. That's what the system does. Okay, so what is x hat? Well, here's the definition. Ax1 of t plus bx2 of t squared. And now we can square this whole thing out. So we get a squared x1 of t squared, x1 squared of t, plus b squared x2 squared of t, right? That term squared and that term squared. A lot of squares going on. And then we have plus 2 times the cross term, which is ab x1 of t, x2 of t. Okay, so that's what we get. I don't see a great way to simplify that any further. So let's jump to the end and say, all right, well, what did we want to see if this equaled? We wanted to see if this equaled the same linear combination of the outputs. So let's look at that. Want to compare to the same linear combination of the outputs. So a y1 of t plus b y2 of t, okay, which we know is a, what was y1? Well, we wrote it already. Oops. It's x1 squared of t. So a times x1 squared of t plus b times x2 squared of t. And we say, okay, is this always for any x1 and x2 and any a and b equal to this? Well, I would say pretty clearly no. I mean, these look radically different. There is no possible way you could change one into the other. I mean, even these two terms are different, and this term is completely missing. These are clearly different, and so you would be tempted to conclude already that the system is not linear, and it turns out here you would be right. And you could even think about that from the very get-go, because I mean, squaring is sort of a non-linear operation. Okay, we're taking values of x and squaring it, so you could have kind of gotten that intuition initially, but I really want to emphasize proving this rigorously, because as we saw in the last example, sometimes you can get surprised and things that look different are actually the same. But okay, so these clearly do not seem equal in general. So these are not equal in general, but we want to be really for sure 100% positive that the system's not linear. And so to do so, you always have to find a specific counterexample. Okay, so to show something is linear, we have to show for any choices of all of these variables, this thing holds. Okay, to show something's not linear, you just have to find one specific counterexample, one choice of these variables that make this line not hold. So to be absolutely sure it's not linear, we've gotten to this point, we're pretty sure it's not. Let's just come up with a specific counterexample. Okay, and let's try and make it as simple as possible. All right, so what seems to be one possible issue here? Well, one issue is that we have an a squared versus an a. Okay, so maybe we can get away with only looking at part of the linearity definition. Okay, so if you can find some way to check linearity more easily, you're absolutely allowed to do that, because if you just set b to be 0, I did this in a previous example, to set b to be 0, this property has to be true, that ax1 has to give me ay1. So even if you can find an a and an x1 that make that part of linearity not true, then you're set. That's a counterexample and the system can't be linear. Let's think about how to do that. And you can think about it on your own too. But I'll just jump to example I thought of. There's infinitely many. But let's make it really simple. Let's suppose our x of t is just 1. Okay, let's suppose our x of t is just 1. And that's not just the number 1. That is the signal that is always 1 for all time t. Okay, that's what x of t is. X of t is always 1 for all time t. What happens when we put that into the system? Well, we get out x squared. We get out 1 squared, right, which is just 1. Okay, and this is going to be, here I'll call it, we get out y of t, which is x squared of t, which is 1 squared, which is 1. Okay, now let's see what happens when we put in some constant times that function. Let's see what happens when we put in, say, 2 times x of t. Okay, what happens when I put in 2 times x of t? Okay, well, what do I get out? I get out that whole function squared, right? Let's call this a new name just so we're all on the same page. I get out x hat of t squared, oops, not equals. Yeah, x hat of t squared, that's what we did above. Okay. And x hat is 2 times x of t squared, which is 4 times x of t squared. And remember, x of t equaled 1. X of t also equaled 1, or sorry, x of t squared also equaled 1. So I just get out 4. So I put in 2 times x of t, and I got out 4. Okay, actually, we don't even need x of t. We can just use a specific a and we get the answer, but actually, no, it's better to have a specific counterexample. So we just get out 4. This is good. Okay, now let's compare this, right? We put in 2 times x of t. Let's compare it to what we should get if it's linear. If the system were linear, output would be, well, we put in 2 times x of t, the output better be 2 times y of t. But look, y of t equals 1 as well. So this is just 2 times 1, which is 2. You can see that these are not equal. Not equal. Okay, so just to summarize, this was our specific counterexample. We said, what if x of t was 1 and a was 2? And then we just went through the linearity check for that specific counterexample. We saw that when we put in 2 times x of t, we got out the signal 4. If the system were linear, the output would be 2 times y of t, right? The same linear combination of the output as we had for the input, but 2 times y of t by calculation is just 2. And 2 and 4 are not equal. And so there we go. The system is not linear. Okay, so definitely, take a moment and try that, go through that logic again, because this is really important for the class. Go through all of that logic, make sure it makes sense, make sure you understand why this is proving the system is not linear. Okay, so I'm going to move on for now. So let's check time invariance. So we know how this goes. We're going to suppose we have x of t, and it gives us some output y of t, which we're in the squaring system, so this is x squared of t. And now we want to check what happens when I shift x by some amount in time. Again, I'm going to call this x hat of t. And we know what comes out. We've done this many times at this point, x hat of t squared. And what is x hat of t? Well, we see that it is x of t minus t naught squared. But of course, that's the same as x squared of t minus t naught, right? I'm just taking a function and squaring it. This is just a different way of writing it. Now you see, wait a second, x squared of t minus t naught, that's exactly my y with t minus t naught plugged in. I just plug in t minus t naught there. I get x squared of t minus t naught, which is exactly what I have there. Okay, and this is exactly what time invariance wants us to show. That if I shift my input by some amount, I get the same output I got before, y of t shifted by the same amount. So yes, the system is TI. Okay. So that was pretty okay. Okay, last example. Okay, we have an x of t goes into a system. What comes out? Well, we're going to flip it. Okay, we're going to get out x of negative t. So we take the whole signal and we flip it about the vertical axis. Okay, that's what the system does. So for linearity, it's very similar to what we did before. Okay, I'm going to say check on your own. Very similar to what we've done before, but it is linear. Okay, so you can check that, but time invariance is the one I want to go through. So we know the setup. We're going to suppose x of t goes in, and I get y of t out. And I know what it is. It's x of negative t by the system definition. Then let's put a time-shifted version of my input, x of t minus t naught. And here I'm going to call this x hat of t. And in this example, I think this step is extremely helpful. If you didn't have this step, I think it would be tough to think through what's happening. But we're going to rename our input as an arbitrary function here, x hat of t, okay, because that allows us to easily get the output. We know that the output now is x hat of negative t. Because otherwise, if I told you find the output of this to the system, it's a little confusing. Where does this negative go? It's a little confusing. Okay, I'm not exactly sure. Do you just negate t? Do you negate this whole thing? So we're going to find out right now. So x hat of negative t, what is that? Well, look, everywhere, all I'm doing here is plugging in negative t to this argument. So everywhere I see that t, I'm going to plug in negative t. That's what it means to plug into a function. I'm going to plug in this negative t everywhere I see t in this function. Okay, so what do I get? I'm going to get x of negative t minus t naught. Okay, a lot of students get confused on this step. Make sure you understand. I have x hat of negative t. Here's the definition of my x hat function. Everywhere I see that t, I'm going to plug in negative t. So there we go. I plug it in right there. And so we see now that the output from the system is actually x of negative t minus t naught. And I think it would be tough to reason through in your head exactly why that's the case using some other method. I think this is the clearest and cleanest way. Okay, so this is the output from our system. And again, let's compare this to what time invariance asked us to check it against, which is the output I got before, y of t, but shifted by the same amount. What is that? Well, now I'm going to do a similar thing. Okay, I'm going to take this t and plug it in everywhere I see that t. Okay, so I'm plugging in, sorry, not this t minus t naught. I'm plugging it in everywhere I see that t. And you can see that that t minus t naught goes in for that t, and the negative is outside of it. Okay, this is the crucial step. So I get x of negative and then the entire thing, t minus t naught. Okay, make sure you understand the differences between going from that line to this one and that line to that one. And if you don't, then all of these problems are going to be pretty troublesome. Okay, so make sure you understand exactly how we plugged in for these functions. Okay, so what do I get here? When we just distribute the negative, I get x of negative t plus t naught. Negative t and the negative goes and multiplies that. And I get x of negative t plus t naught. You can see that these two are clearly not equal in general. Okay, and if you want, you can come up with a specific counterexample, but this function is so clearly not equal to the other one in general. I mean, one of them we're subtracting t naught, when we're adding it, almost any counterexample you try to write down is going to fail here. Okay, if t naught was 0, then we'd get the same thing, but probably almost any other function, any other t naught value would get these functions to be different. So you can think about that on your own. But I think we can conclude at this point that those are clearly not equal in general. One of them is minus t naught, one is plus t naught. Okay, so now we can say that this is not time invariant. Okay, so that's a really important example. I hope you look away and try this on your own again to make sure you get it right. Okay, so that's it. We did a lot of examples here. I hope it was really helpful and you get a feel for how these properties are proved. And the only thing that I've not done here is find a system that is both non-linear, so it's not linear, and it's not time invariant. I've done all of the other examples here. Okay, this one was linear and not time invariant. This one was not linear, but it was time invariant. And the first two were LTI, linear and time invariant. So for an exercise, try and come up with a system that is not linear and not time invariant. So I'll leave you with that. And that's all I have for this video. I will see you in the next one.